All right, let's get going on this snowy afternoon. I did not expect the snow. I looked at the weather report and I didn't expect the snow, but oh well, it's out there. All right, so we're going to talk today. Today's the 3rd of February, and we are going to talk about a number of things today. I'm going to give you a Unix tip of the day, which will hopefully help a little bit on this week's homework assignment, which is also on the agenda today. Homework assignment 2 is out today, due a week from Tuesday night. So hopefully that'll be enough time. We'll go over the basics of the assignment. And also lab 2. A couple people just got done with lab 2. Did you guys finish it up? Did you get it all finished? Good. It was. I hoped it was. It's a little tricky, a couple parts of it, but it will prepare you for this week's homework assignment as well. We'll talk about that too. I've got a comment on reversing linked lists. Yesterday or last week, Margaret made a good comment that I answered, but then realized a little bit later it's a little more tricky. So I'm going to comment on that in a minute. And then we'll get into today's big part of the lecture, which is on recursion, which I understand most of you guys have seen before. And those of you guys who did Comp 50 should be really familiar with recursion. So we'll do a little bit of it. It'll be a review for some of you guys, and maybe we'll see some new stuff as well. So that's that. OK, a comment on linked lists. So the other day, we were drawing these doubly linked lists, and we kind of finished up and we said, hey, how would we go about reversing this list, right? So if this is the head here and the tail is all the way over here, how would we go about saying reversing the list so that this becomes the head, everybody else goes down, everybody else gets their pointers swapped, and then this ends up as the tail. OK. And Margaret brought up a good point. She said, hey, what if we went down through the linked list one direction and changed all the ones going one direction, and then came back and changed all the ones going in the other direction? OK, and I said, oh, it's not a bad idea. You go through the list twice, but it's not a bad idea. There is one part to that which is probably not going to be as easy as you think. Any idea what it is?
When you go back through, how do you know which one?
When you go back through, how do you know which one? You've kind of lost that data, right? Good, very good, Margaret. So what she's saying is, OK, you go through this one and you say, all right, I'm going to go through the list this way and change all the forward pointers or whatever to be this way. Well, you've got to keep that forward pointer. That's one thing. You have to keep you can set a temporary variable and go through and then change this one to now point back to this one. And well, you can't really, actually. You've got to basically say the next. Well, yeah, I guess you can. The next one has to be the previous one. So you've got to be really careful that you don't accidentally go through and change the ones that you need to follow on the way back. That's the only problem with that, OK, besides going through the list twice. So I just wanted to comment on that. That was a very good suggestion, but there are a couple things like that you need to be wary of. And finally, we will talk about linked lists, doubly linked lists in this week's lab as well. And so you'll get a little more familiar with how to deal with changing all those pointers up. OK? All right. So let's go to the Unix tip of the day. So here's the tip for today. One of the things that I've given you in this week's homework assignment, some of you guys noticed that it was actually posted last night. It's on there now. It's on the website. You can pull it down and take a look at it. I haven't printed it out because it's like 5 pages long, and it's just a bunch of, it's got a lot of code in it and a lot of instructions. But one thing that I've given you in the files that you'll get is sample output from the program that you're going to create. So in other words, I've given you a file, and it's got output that we want your output to match. When you run your program, we want it to be exactly like that output. Fair enough? So the reason we're doing that is because the last time, if you'll remember, during when you did the rectangles, some of you guys did had extra output that didn't make it through the auto grader, right? So it flagged it and said, oh, the output's wrong. Well, the output was fine. It just had extra stuff in it, or didn't have the right new lines or whatever. So now you're going to be able to compare your output directly to the output that I give you in this text file. OK? But how do you actually go about comparing these things? OK, there's two things that you can do there's two things that you need to be able to do. We're actually going to go to the second one here first. There's this command called diff, D-I-F-F. It's a Unix command, and it's pretty cool in that it takes two files and tells you if there's any differences between them. OK? So let me show you what that's all about here. OK? So here's what I have. I actually have a couple files on here. Actually, there's 4 here, but these are the ones I care about. I have one called jackandjill.txt and Jill and Jack. And you guys know the nursery rhyme, Jack and Jill climbed up a hill to fetch a pail of water, right? In fact, I've got it right here. LS Jack, not Alice, sorry. Less Jack and Jill, and this is what it says. Jack and Jill climbed a hill, should say, climbed up a hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after. What I did was I took this, and then I just swapped Jack and Jill, right? Who says Jill had to be the one tumbling after? Maybe it was Jack, right? So if you do less Jill and Jack, you get this. Jill and Jack climbed up, it doesn't rhyme anymore. It's the only problem, right? Jill and Jack climbed up a hill, or a stack or something, to fetch a pail of water. Jill fell down and broke her crown, and Jack came tumbling after. Now, those 2 files are similar, but they've got differences, right? Specifically, they've got differences in the names. And the only line that's actually the same in both files is this one, to fetch a pail of water. Okay? What I can do is I can say, if I clear this, I can say diff, and then I can say Jack and Jill.txt, and then I put Jill and Jack.txt. And what it comes out, and don't be scared by what comes out here, but what comes out is it says some numbers which designate the line numbers that are changed, actually, in a range of line numbers. This says from 1 to 1. Jack and Jill climbed up a hill, right? This is what it changed to in the other file. Jill and Jack climbed up a hill. So you can tell, you can say, oh, look, line 1 is different. These 2 lines are different. This one says lines 3 and 4 are also different. Jack fell down and broke his crown, and Jill came tumbling after. It should be Jill fell down and broke her crown, and Jack came tumbling after. So that's what it's changed to. Okay? You can also do diff with a, let's see, a -u, right, which is just a slightly different format, and it gives it to you right after the other. It says some other stuff here about the line numbers. Then it says, look, Jack and Jill climbed up a hill minus plus in the other file is Jill and Jack climbed up a hill. So those are the 2 lines next to each other. What this doesn't really tell you, what it doesn't show you is the space differences. Like it just doesn't show you that there's maybe a space on the end of one or the other. But you can see that there's a difference in the line. So at least you can tell, oh, the line must be different. And then you can go back and look. Oh, you can tell. Okay, so that's how you actually do the difference between 2 files. Okay, it will also tell you the difference between 2 binary files like programs, but it won't tell you what the difference is. It'll just say files are different. That's all it tells you. So that's that. How do you get your output from your program into a file where you can compare? Well, that's what the other little thing here, oops, that's what the other one here is, this greater than sign. What you do is you run a program. So in here I have a program called hello world, ./hello world, and when I run it, it just prints out hello world. If I do this, if I type hello world and then greater than sign, as if I'm pointing the output to a file, and I give it some file, hello output.txt or something like that, right? It looks like it doesn't do anything, but it actually does. It actually takes anything that was going to be output from your file, from your program, and ends up pushing it into a file called hello output.txt. So cat hello output.txt, and there it is. So now it's in a file, and you can use the less command to check it against your other stuff, the other file that I've given you. Make sense? You can check the notes online if you forget how to use these. Well, just need to remember diff and the greater than symbol. Okay? Don't make the greater than symbol go into a file that already exists, or it will delete it and put your stuff in there. Just be careful with that. It's the only caveat in that case. Okay? All right, questions on Unix tip of the day? Awesome. OK, so homework 2 is on ordered lists. All right? And what this assignment is about, the other day I mentioned that we were talking about, we're going to be doing a little calendar app. It's just like the calendar in your phone or Google Calendar online or whatever. And we're going to have this little program take events and put them into days, just like your calendar might. Okay? And in fact, we're going to have it so that it exports to your own Google Calendar. Okay? We're going to be building this thing called an ordered list. Now, when we talked about lists before, right, we didn't really necessarily care that they were in any particular order. It didn't actually matter what the order was. Right? We could say, we would put some values in to the list, right? And We could put 3 and 2 and 5. Now what we're going to do is we're going to say, hold on a sec. When we build these lists, we want the list to be ordered in our case, by the start time of this event that we're talking about. Okay, so we want them to be always in that order. We call this an invariant about our list. Okay, we call it an invariant. What an invariant means is that when you're dealing with the list, it should always be following that invariant. In this case, the invariant is it's going to be an ordered list. So the list always has to be ordered. Well, when you get done manipulating, it has to be ordered. Okay, so if we were to insert something here, we're going to say 2 and then 5. And if we're going to insert 3, well, 3 better go where 5 was, like that. We have to insert it properly. Okay, so that's how this is going to work. You're going to have to take these events and keep them in this ordered list. Okay, that's what the invariant means. And we'll be using the term invariant a lot during this course, because it's true for a lot of different data structures. You have some invariant that makes it so that that object behaves the way it does. Okay. The ordered list we're going to be using is called an ordered list of events. Obviously, we're doing calendars, so we're going to have an ordered list of events. And the events are going to have 3 different private data elements, right? It's going to have a start time of the event, an end time of the event, and some description of the event. Okay? So let me do it like a calendar might be on some day, right? We're going to do this. Okay? We're going to have a list of events here. Okay? And then each event's going to have start time, end time, and description. So let's say you get up in the morning and every morning you put in a calendar, you're going to go for a run, right? Because everybody here works out, right? Yeah. You're going to go for a run, right? And you're going to put this in your calendar. And let's say the run starts at 0800, and then it goes to 0900. And we're going to use so-called like military time or 24-hour clock time, where 0 means midnight and 23:59 means 11:59 p.m. Okay? So, and 0800 is 8 a.m. and 0900 is 9 a.m. So from 8 to 9, okay, you might say run. Right? That might be your event. And that's all the event class is going to have in it in terms of data. Okay? That's all it's going to hold. And we're going to keep this ordered list in order by the start time. Okay? We're going to keep it in order by the start time. We're not going to care if there's any overlaps in the times. It's just whatever the start time is. Okay? We're going to do that. All right. Events also have a couple other details about them. They actually have standard getters and setters, like most classes. Then they have a few methods, right? Not too many, but only a few. They've got one method is called am I before some other event. Okay? So, by the way, let's fill in the details here. If I was going to say, let's say you're going to have lunch in here somewhere, right? If I was going to say lunch, I'm going to put it down here. So let's say 1200 to 1300. That would be 1 p.m. Lunch. Okay? And then let's say you're going to have data structures class. Okay? Actually, I should have put it up one. Data structures class is going to come in here, and data structures is from 1500 to 1615. So 1500 to 1615, 3 to 415, and that's data structures class, like that. Okay? All right. The am I before method is going to be run on an event. So let's say I have a lunch event, LUNCH, like that. Let's say I have a lunch event, or it could be a pointer to a lunch event or something like that, right? And we'll get to how you reference those differently in a minute. If you say lunch dot am I before, right? And then in parentheses you put, say, run, because that's another event, let's say. Lunch am I before run would be false, because lunch is not before the run. It's the lunch am I before the other event. Okay, makes sense? Why do we do that? Because we need to compare these. Okay, and again, the am I before, all it does is compares the start time. So if lunch starts before run, then it would be true. If lunch starts after run, then it would be false. Okay? Any ties, you're going to say that it's false. Okay? The reason we're going to do that is so that if they happen to start at the same time, the next one you put in is going to be after the first one. Okay? And for those who did the lab, this is kind of familiar to what you did during the lab too. You'll see for those of you who didn't. Okay. Now, there's another method here called is same event as. And that takes another event as well. Okay? Is same event as is different in that the event has to be the same details. So it has to have the same start time, the same end time, and the same description. Then we say that it's the same event. Okay? It's not just the time. So in order to compare in the is same event as class, how are we going to do that comparison? What do you guys think? What are we going to do to the different parts of these events? You don't even need to do a for loop in this case. There's three parts. Remember, there's three parts, right? There's a start time, an end time, and a description. And if you want to see if two events are the same event, you have to compare all three of those. So it's easy enough to do. You say is like lunch dot start time equal other event dot start time, that sort of thing. Okay, so that's pretty straightforward, I think. There's also going to be this event called print event. Now, print event, it's just going to print out what your event is. It's going to say like start time 0800, end time 0900, and then it's going to say description. It's going to say lunch with an H on it. There we go. So that's what it's going to say when you print out an event. You say like lunch.print event, and it's going to say start time, end time, description. That's it. Okay? And then finally, events also have this odd one called event CSV. Does anyone know what CSV stands for? There you go, comma separated value. This means that your event is going to be just a string, and it's going to print out like this. It's going to be 0800, comma, 0900, comma, lunch. And that's going to be your comma separated value. Why might we do that? Why do we care about a comma separated value? Yeah? Yeah, it probably does. The answer was the Google Calendar API probably accepts comma separated variables. When two computers talk to each other, which happens, as we said the other day, happens all the time. When two computers talk to each other, they need to have a common way of passing data back and forth. One very common way is this comma separated variable or comma separated value list. Okay? So Google Calendar may say, hey, I want an event, and you pass in 0800, 0900 lunch with commas. It knows this is the start time, this is the end time, and that's the description. Right? What might be a problem with this if we've got comma separated value lists? Anybody see a problem with this? Yeah. Yeah, if the description contains a comma, then you're in trouble, right? Like you say lunch, make sure to eat your vegetables or something, and you put comma in there, right? Well, then maybe the computer might say, hey, there's an extra comma. Is this supposed to be some other field? So you can do that. We can take care of that by just agreeing on what happens when you do get a comma inside something. Normally what you do is you put two characters and you say it's like some other backslash or something like that that says, oh, this is going to be a special comma. But anyway, that's what a CSV is, and we'll use that when we get into exporting things into Google Calendar. Okay? All right. Yes?
Why is it that we're not keeping track of the day?
Good question. Why aren't we keeping track of the day? We will, but this is just an event, right? And an event, we're saying, can happen on any day, but it's just the times. Okay? The day will come in a little later.
So if you have an event that runs longer than 24 hours?
Yeah, in this case, we're not. We're going to say that no events go over 24 hours in this case. Good, very good question. Yeah, Margaret.
CSV, are those three different strings, or is that one string?
It's one string, and the 0800 gets converted into a string. In fact, it's probably just going to, in your case, it's probably just going to be 800, not 0800. We're not going to worry about that. And by the way, we already wrote this one for you. So you can look at the code and say, oh, I see how they did that, right? But it's not going to be, we didn't bother putting the extra 0 on there. We could, but we didn't do that. So it'll just say 800, 900. Midnight would be 0, just 0. Yeah. Okay. Other questions on the event class? Okay. Then we have the day class. Now, the day class is going to take a bunch of events and keep them in this ordered list. So the ordered list is where the day class comes into play. Day class is going to have actually 4 different functions, or 4 different methods. It's going to have a schedule event method. Now notice it's got 3 different varieties. This is exactly like constructors. We've just overloaded this method, which means that we allow it to have different parameters here. Okay, so you can call schedule event, which just makes an event for the whole day. You can call schedule event with the individual times and description, or you can call schedule event with another event. So what it does is it copies that other event into your new event. Well, it takes that and copies it into the day where it needs to be. Okay. We can also cancel an event. So you come down and you say, you know what, lunch isn't sitting very well with me. I'm going to cancel data structures. I'll watch the video later or something, right? So we have to go and cancel the event. And this is the part where we need the is same as method, because you need to figure out which one of these is the one you need to cancel. You pass in some event that you need to cancel, and this is the one that needs to get canceled. Okay? All right. And then we've got print day. Print day is really easy. It just says to all the events, runs through all the events and says print event. And that's all that is. And export day is the same idea. It goes through all the events and says export CSV, or whatever the name was. It was event CSV. So it says event CSV, and it gets a list of a bunch of comma separated values, 1 on each line. And that's what that does. Okay, so those are the only ones you have to write. And then you have to write the destructor, which is there. Okay. So I say those are the only ones you have to write. You do have to do this twice. Okay? What it is we're going to have an event class, and we're going to have 2 versions of the day class. So we've been talking about 2 different types of lists in here. We've been talking about the dynamic array type list. We've also been talking about the linked list. The linked list, both those lists, you're going to have to make into separate day classes. But the cool thing about this is it's going to be such that, depending on which one you want, you don't have to change either the main function or the event class at all. Both day classes will use this, and both day classes will have those methods in them, and you won't have to do anything else. Okay, you just have to put those, and you can. The way you get it to run either one or the other is you just tell the make file, make this one, make the one that's a linked list, or make the one that's the dynamic array. Any questions on that? We'll get into the details of that. Well, you'll get into the details when you start looking at it. But you need to do 2 different implementations, so you get practice on both. Okay, interchangeable. All right. Questions on that? Okay. All right, a couple other things here. So, and this is primarily for people who forgot about how to reference pointers versus objects. Okay, I won't spend too much time on this. But if you have, there's a different way to access the methods of a various object, whether you have a pointer or if you have the object itself. So if you have the object itself, right, you use this little dot symbol. Okay? So what that means is, I have the next slide actually talks about it. But what that means is if you have an object that's not a pointer, you just refer to the methods by using dot and then the method name, like getTime or getStartTime. Okay? Something like that. You use this little arrow notation, which is a dash and then a little greater than sign, to refer to the members of the class if you have a pointer. Okay? So if you've got a pointer, if you've got an object n that's not a pointer, you do n dot member. If you have a pointer, you do p arrow member. This is exactly like saying star p in parentheses dot member, because this tells you get me the object at that address. Okay? Normally we'll use this because it's a little more clear, and it also tells you, hey, I'm using a pointer. So this is probably the easiest one to use. And you got to get used to when to use one or the other. Okay? In the lab today, you have to do one versus the other more frequently. You have to do both, but you got to get used to it. Okay? All right, here's the example. If we say we have an event called breakfast, and we declare it like this, event 900, 1000 breakfast, right? And you do it this way, that's giving you the actual event object. So it's not a pointer, and you can tell there's no star over here. And you refer to the getter for start time as breakfast dot, well, it's actually breakfast dot get start time, I believe. Okay? Then if you have a pointer, it looks like this. New event with the star for the pointer equals new. And remember, new always gives you a pointer. New event, and same thing. Now you've got a pointer. Now you have to say new event arrow get start time or start time. Okay. Questions on the differences? Guys all got that? If you mess it up, and if you accidentally use the arrow when you should be using the dot, the compiler will tell you. It'll say, hey, this doesn't make sense. And so you'll just switch it. So it's not the biggest deal in the world. Okay? All right. Let's see. I think that's about it for the homework assignment. Due next Tuesday night. There'll be lots of office hours. You can get working on it. But I would not wait too long, because it is that you'd have to write a fair amount of code for it. Not too much, but a fair amount. Okay? And the lab will prepare you for that by making you use a linked list today. Actually, a doubly linked list. The one we're going to use for the day class is going to be a singly linked list, not a doubly linked list. Okay? Yeah, singly linked list. Okay, not a doubly linked list. If you for the lab, it's a doubly linked list, so you'll get extra practice in that. Okay. Questions on any of that? Homework, lab, other stuff before we go into the new stuff? Okay. Take a look at this. So recursion, which I gather most of you guys have seen in Comp 11, or of course in Comp 50 you saw a lot of recursion. This little kind of joke says to understand recursion, you must understand recursion, right? Well, it's all about referring to yourself in some way or another. Yourself being an object or a method or whatever. Okay, that's what recursion's all about. Google has a little joke on their Google webpage. If you type in recursion into Google, it actually says, did you mean recursion? Right? And you go, oh yeah, I meant recursion. You click on that, and then it takes you right back to the same page, and it says, did you mean recursion? Right? Because what they're saying is, your recursion means to refer to yourself. So it's saying, all right, did you mean to refer to it? So I should probably never explain a joke, right? If you have to explain a joke, forget it. But anyway, that's the whole point. So they've got this little joke in there. They're computer scientists. They like this thing. Recursion, as you can see from the Wikipedia blurb here, recursion is the process of repeating items in a self-similar way. For instance, when the surfaces of two mirrors are exactly parallel to each other, blah, blah, blah. You've ever been in a place where there's two mirrors, one in front and one in back, and you stare into one mirror, and you see mirror, 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 right? That's analogous to this idea of recursion, where you've got one thing repeating itself after another, after another, after another. And it goes on for infinity. Right? I mean, well, you always kind of look, can I see the last mirror, right? Excuse me, but you can't, because it just kind of keeps on going on until you can't see it anymore. That's the basic idea of recursion. Okay? In computer science, what recursion means in computer science is that a function will call itself. Okay? A function calls itself, and this is a terrible example. But it's a very basic example of what you could do to use recursion. You could say int main and then main. And what this tells the compiler is it says, OK, I'm in the main function. I'm going to go to the next program. I'm going to call this function. Well, this function is called main, and the compiler is perfectly happy to go back and start over here and say, OK, now I'm here. What do I do next? Oh, I call main. OK, that means I start here, and it'll do that forever. In fact, if you ran this program, it would go and segfault on you. OK, and it would segfault on you after not very long. It would not take too long to actually do that. And here's why it does that. You'd think, oh, well, who cares? It's just like a loop that goes forever and ever and ever. Not true. Whenever you call a method or a function in a computer programming language, the computer has to say, stop what I'm doing and go do this other thing. In other words, stop this function that we're in here, and go do this one. Well, this happens to be the same one, but it's got to save whatever the computer's doing at that time, so that it can come back to that later and keep going from where it left off, right? So in this case, main, when you get to this line, the computer says, stop, save what I'm doing, and store it in memory, and that takes up some memory, and then go and do this again. But notice it keeps doing it forever and ever and ever. That takes up more and more and more memory. Eventually, the computer says, I'm out of memory, I'm done. And it actually does not take that long to do. Okay? You'll see when we run one in a second that's similar to this. Okay? Questions on what recursion looks like in the very basic general sense? Okay. Here's how you would solve a recursive thing in real life. We don't really solve recursive things in real life too often. Like, we don't have recursion in our natural lives too often, right? But here's how you might tell somebody to solve a jigsaw puzzle recursively. Say, hey, solve the puzzle. Here's your steps. OK, step 1, is the puzzle finished? Stop. Right? If you're looking at the puzzle and it's done, you can stop solving the puzzle because it's already done. But if it's not done, you go to the next one, you say, find a correct puzzle piece and place it in the puzzle. All right, easier said than done, right? You can't just take a piece and put it where it needs to go, but let's say you can, right? And then the last step is solve the puzzle, which means go back up to the top and start over and say, is the puzzle finished? If so, stop. Now it's not finished, I just put one piece in. Find a correct piece, there's one, put it in the right place. Solve the puzzle. That's the recursion that we're talking about, okay? That's the recursion, all right? And again, we don't do that in real life. I kind of struggled to find a real life example, but you know, there are probably some others that you could use. OK, here's another terrible example. I'm full of these today, right? Here's another example. This example says, it's called Recurse, not a very unique name, I suppose. It's called Recurse, and it takes an integer as an argument. And that integer, in this case, is going to be called how many. And what it's going to do is it's going to print out that number and a new line, and then it's going to call itself except with how many plus 1. Okay? And if we run this and we say recurse 0, it's going to go through and it's going to be 0 here, and it's going to say print out 0. Recurse with 1. Go back up, run this again, print out 1. Recurse with 2, print out again, and keep going on. Is this ever going to stop? It will stop when it segfaults, right? Take a look. Okay, I've actually written this here. Let's see. Here we go. Recursive count up forever. Anybody have any idea what number it's going to get to, roughly? I'm going to throw out some numbers. Yeah.
4 billion.
4 billion. Good guess. 1,000. 1,000. Good guess.
Yeah, 5.
5. Good guess. Not quite as good as the others, but good guess. All right, let's see. All right, so it's going to print out. It's going to go up. Oh, it actually only made it to 262,020. Right? Now, the question is why? Well, each program is actually given, yours is a pretty good guess, all things considered. It is closer than 4 billion, but it was too small. But anyway, it is closer than 4 billion, that's true. So what it does, basically your program only has a certain amount of space, and it takes a certain amount of memory to actually store this. Because of the way programs are kind of compartmentalized, each program is only given a certain amount of stack space, we call it, which is where the actual program stores all this saved data about when it gets called. So in this case, it does this. If I had done this on the homework server, it would have been a totally different number. This just happened to be my own computer here running the Apple operating system, right? But you can see it did segfault. Okay, not so good when you're trying to keep a program running. Okay. So this is a bad example. The problem with this example is what? Yeah. There's no stop case. Exactly, right? We just keep going and we never say when to actually stop doing this recursion. And that's a really important part of doing these recursion things, okay? So let's do this one. You've probably seen this example before. If you haven't, great. How to count down recursively from n to 0. So let's do this. Let's count down from 3 to 0, including 0, right? Here's the little algorithm. Is n less than 0? If yes, then stop. There's our stopping condition. Say the letter n, or print it out in this case. Count down from n minus 1. Okay? So if we say count down 3, we're going to do the first thing. Are we less than 0? No. So we say 3, or we write it down. And then count down from n minus 1, which is 2. And then we do the same thing. Are we less than 0? No. 2. Go do the same thing. Count down from 1. Are we less than 0? No. Count down from 0. Are we less than 0? No. Do 0. And then count down from negative 1. Is n less than 0? It is. We're done. But that's how you count down from 0, or to 0 from a number, okay? Recursively. Here's the actual program to do it. Okay? Count down, int count. If count is less than 0, return. It's exactly like the algorithm we just said. Print out our count, and then count down from count minus 1. Will this one stop? I hope so, right? This one logically makes sense. It's got what we call a base case. Okay? A case that we're going to check for, and the program's going to kind of aim for that case. When we get there, that's when we stop. Okay? That's how we would count down. We'd have this base case, and we recursively do this. Great. Is there a way to count up recursively? What's that? if you choose a stopping point. So when you're counting down to 0, the nice thing about it is counting down to 0 always ends up at 0, right? It always ends up at 0. Counting up is a little trickier because you can count up to 100. You have to stop at 100. You can count to 200. Well, you have to go past 100 and you have to count 200, right? And you have to go, if you want to count to 1,000,000, you've got to go all the way up and stop at 1,000,000. There's no case where it's aiming towards. Okay? But I do want to show you a sneaky way of counting up to 100 in this case. Okay, so or any case, we want to count up to some number. How do you count up with recursion? Turns out, using this program, if you move one line in this program, it will actually count up instead of counting down. You don't need to change any numbers. You don't need to change any logic. You just need to change one line. Can anybody see what line it is? If you can't, that's all right. Take a look at it. I'll get you in a sec. Anybody else think they know? Yeah.
If you put out the cout below the recursive call.
Yeah. Was that what you guys were going to say too? If you put this line below the recursive call, let's see what happens. Okay? And in fact, I think that's the next little thing here. There it is. Swap those two lines, right? And all I'm doing, I changed the little thing to say count up, but that's all I changed. I didn't actually, it could still say count down, and this would actually count up, right? And what we did was we swapped these two lines. So what's happening now is if we were to talk through this, right? It would be like this. We would say, OK, count up from 3. If count is less than 0, return. We've still got our same base case, believe it or not. Count up from 2. Did I print anything out yet? No, I haven't printed anything yet. I just said count up from 3. Now count up from 2. This is where we're saving the state, and we're waiting, and we're going to this line next. Well, that means I go and I redo this. Now I say count up 2. If it's not less than 0, count up 1. Have I printed anything yet? I have not. Count up 1. Go down here. Nope. Count up 0. OK, go up here. Is it less than 0? No. Count up -1. Now we're at -1. We haven't printed anything out yet. Now we get down here and we say, is count less than 0? Yes, it's now -1. So we return. Where do we return to? That's the question. Where does this actually return to when it does it? Yeah?
Where it stopped in the first iteration.
Yeah. Well, actually, in the last iteration is where it stopped, right? So in other words, it's going to be here and say count -1. And that -1 case is just going to return, and it's going to end up here. And this is going to say print out 0, because that was the last thing it asked for before it got to this count. Because it's going to print 0, right? It's going to go whoop, 0. And then this function that we're doing now is going to end. And that means it's going to return to the previous function, which it asked to print out 1. So it's going to say 1. And then that one's going to end, and it's going to return to the other one. It's going to print 2. And that one's going to end, and it's going to return. It's going to print 3. And then that one's finally going to end, and we're done. You see how it kind of nested itself? I'll write it a slightly different way. Okay? First we said count up 3. Before this does anything, this calls count up 2. And then this calls count up 3. Or sorry, 1. And then this calls count up 0, and that calls count up -1. After this gets done, after this one gets done with counting up 2, which happens after counting up 1 and after counting up 0 and so on, it gets back here, and then it says, oh, I finished that line. Now print my number. And you see how it's going to end up printing it increasing instead of decreasing? Yeah, a little sneaky. Yeah.
Seems like it would just print 0 over and over again. Like if it's just doing the function.
Take a look at what it says it's to print. It prints count, right? OK. The first time through, what is count? No, the first time through. Let's say I start at count up 3. First time through, it goes here and it says if count is less than 0, count is 3 right now, right? OK. It says it's not, so it's not less than 0. So it's going to tell the computer count up from 2. It hasn't printed anything yet, right? It's going to save everything in this while it calls the other count up again. And it's going to say, right now, count equals 3. And I'm saving that. And then I'm calling this with 2. And then it's going to call that with 2. And then it's going to call it with 1. And then it's going to call it with 0. And then it's going to call it with -1. And then it's going to start returning. Boom, 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 boom. By the time it gets back to the 2, 1 printing out, this line ends. And remember back how we saved what 3 was. It gets to here. And it says, I'm done with this line. Everything's the same where I left off before. Now, print out count. Well, count was 3 when I saved it. So that's why it's going to, at the end, print 3. It's not going to print 0 because count actually changes. This is where the scope of the function comes into play. In other words, in this function, count has a certain value. Outside this function, all bets are off. Count can be a completely different value outside of this function, even if it's the same count up function. Saves all the state, moves on to the next thing, does its thing, saves all the state, moves on to the next thing. And then as it goes back, it replaces what it had saved. Make sense? OK. Other questions on this one? All right. Good. OK, so that's how you count up and count down with recursion. Let's look at a couple other examples of recursive functions. Okay? We'll do a couple on here. I think we'll only get through a couple. But we'll test a couple of these ideas out. Remember 2 things about recursion. Okay? The first thing you need to remember is you need that base case. You need to know, where am I going to stop? You have to figure that out. The second thing to remember is, how can I break my problem into a slightly smaller problem than the one that I started with? Okay? Those are the 2 things that you're kind of trying to do so that this recursion thing actually works. Okay? Let's start out looking at, the power function. Okay? Okay. You guys all know what this means, obviously. If you're taking b raised to some power, okay, that just means the following, right? That means b times b times b dot 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 times b, where the total number of b's here is just n. Okay, that makes sense. That's just what the power function, that's what it does. Okay, that's what b raised to the n power means. Okay. We could rewrite this, though. If you rewrite this, you could say b to the n equals b times, and I'm going to move over just a little bit more, b times b times b times b dot dot dot, where this is now n minus 1. That makes sense? Right? So far, so good? In this case, okay, we've now taken this and said, aha, we've now broken this down into a slightly smaller problem. Instead of multiplying n times, we now multiply n minus 1 times. This is the recursion part of this. We could write this in a little more mathy way if you want. B raised to the n equals, that was a terrible, terrible bracket. A little better. Okay? What this equals is b times b to the n minus 1. Okay? B to the n minus 1 if n is greater than 0. Okay? If n is greater than 0, that's what the function is. The base case in this case says if n equals 0, it's just going to be 1. Right? Because that's how we've now got the base case there of n equals if anything raised to the 0 power is just 1. Okay? Can we turn this into a function? Of course we can. Okay? We've got the idea here. And the nice thing about recursive functions, if you can write it something like this, writing the actual function is pretty darn easy, as it turns out. Okay? We could say power, and it's going to have to return some value. Okay? Let's make it return a double. You remember what a double is? What kind of type a double is? It's what? It's a double precision floating point, which means it's a really precise floating point. Okay, why not? Okay, double power. Let's also use a double for b and an integer for n. And the reason we're going to do that is we're going to say, look, b can also be any value. It doesn't really matter if these are floating point values here. or right, or fractions or whatever. That makes it, you can still do this. You can't do the n to the minus 1 very easily, right? First time I ever saw somebody do something like 2 to the 1.6, I thought, how is that done? Right? What does that actually mean, 2 raised to the 1.6th power, right? You have to do some numerical methods to actually get this to work, right? It's not as straightforward as the case we're doing. Okay. All right, so in this case, we're going to look at this and we're going to say, all right, we've got our function here. Let's figure out what it is. Well, look, if n equals 0, return 1. If n equals 0, return 1. There's our base case. Okay. Otherwise, and we could have an else in here. You don't actually need it because it'll always return on that. Okay. But you can now say return b times power n minus 1. Whoops. And that's our function. Okay, and it's a recursive function. And let's see how it actually works. Okay, let's walk through this one. Questions on it? Yes?
Doesn't power need 2 parameters?
Oh, it does. You know what? I did the same thing earlier in the class. What's the parameter going to be now? Good question. What's the parameter going to be? B. It's the same b, n minus 1. Yeah, good call. Good catch. OK. Any other questions on this one? OK. So let's look at what happens when we do one of these examples. All right. Let's do power of 2, 3. In other words, 2 raised to 3 power. We're going to hope to get 8 out of it at the end. Right? OK. So here's what's going to happen. We're going to go through this. And the first thing that's going to happen is it's going to call power 2, 3. And we're going to check and see if n is equal to 0. And remember, this is b, this is n. Okay? We're going to check and see if n equals 0. Does n equal 0? No. Okay? So we're going to go and we're going to say return b times power of of n minus 1. In other words, we're going to return, right, 2 times power of 2, 2. Right? There, now we're going to say, OK, well, now we've got it. We're going to recall this function. Let's look at this one. OK, is n equal 0? It's not. So we say we return 2 times power 2, 1. Is 1 equal to 0? We're going to do it again. Is 1 equal to 0? It's not. So return 2 times power 2, 0. Is n equal to 0? It is. So this returns 1. OK. So what this means is now we got to go backwards. And we're done. We're done. We're not calling power anymore. So we can look and we can say, OK, look, return 1. That means that this part was equal to 1. 2 times 1. That means that this is going to be equal to 2 times 1, which is 2. This one's 2 times 2, which is going to be here. 4. 2 times 4 is 8. Right? And that's what this one's going to return. Return 8. OK? You see how that cascades down and then builds back up on the return? OK? Any questions on that? How the power function works recursively? This is not a bad way to do it. There are actually better ways of doing it, but this is not a terrible way. OK? Let's see. Factorial. Factorial is actually so similar that I'm not going to take the time to actually go through it right here. But factorial is almost identical, right? If you're going to do the factorial, like 5 factorial, that equals 5 times 4 times 3 times 2 times 1, right? This is a really easy one to see that it's going to be recursive in that this is going to be equal to 5 times 4 factorial, right? Which is equal to 5 times 4, or 5. It's going to be 5 times 4 times 3 factorial, et cetera, all the way down to 1. So it's actually very similar. Okay, see how that would work? All right. All right. sometimes the recursive solution is not a very good one. Now, what I should first say, and I probably should have said this earlier, recursion is not magic. Like, there is nothing magical about recursion. A lot of times, if you have a recursive solution, what's good about it is that it allows you to have a very easy to understand program, right? It's in some cases a very simple program to understand. That's kind of the beauty of it. It's a very beautiful construct. It's not necessarily the best version in the world. It's not necessarily as efficient or as fast. A, because it has to keep calling these things and saving its state like we talked about. And B, the easy ones that we're talking about here, you could do in a loop very easily. In fact, the compiler will figure out that, I should have left it up there, will figure out, oh, I'm going to convert this into a loop for you. Right? It's going to, in a lot of cases, like the Clang compiler is very good at it. If the last line on your program is return, in your recursive function is return whatever, if that's the last line, the compiler can very easily turn that into an actual loop that doesn't do any of this recursion. Then why do we bother writing in recursion? Because it makes it easier to understand in some cases. So like that's the beauty of it. And if the compiler can figure it out for us how to make it so it is efficient, even better. Right? That happens to be called tail recursion, by the way, when the last thing you do is return. And it's very easy to turn that into a loop. Okay? All right. So the next one I do want to look at is the Fibonacci sequence. Okay? Have you guys do recursion with Fibonacci in 11? So most of you guys did. OK. Well, let's just quickly review. Right? Fibonacci sequence goes like this. Right? You take the two first base case values, which are 0 and 1. Then you take those two and you add them together, right? And you get the third one. And then you take these two and you add them together and you get the fourth one. Then you take these two and you add them together, you get the next one. The next value will be 5, and then 8, et cetera, et cetera, et cetera. OK? Not so bad. OK? You can write this in another mathy way like we did before. I'll abbreviate fib. Fib of n equals, whoops. Here we go again with my terrible brackets. When I took C programming in college, we had to teach our instructor how to do the ampersand. So somebody's going to have to teach me how to do a bracket correctly. There we go. I think taking my time is what's important. All right. So anyway, so in this case, there's two base cases, right? There's the base case if n equals 0, right? So we return 0 if n equals 0. OK? We return 1 if n equals 1. Okay? And the cool recursion part of this is we can say we return the Fibonacci number of n minus 1 times the Fibonacci number of n minus 2 if n is greater than 1. What's that?
Do you add the two numbers?
Thank you. That would be cool. I don't know what that one would be. Some sort of multiplication Fibonacci. You add the two numbers like that. Thank you. So this is what the Fibonacci would look like here. To write this into a function, pretty simple, right? You just say same thing. You'd say fib n. And by the way, n in this case, this is 0, this is 1, this is 2, this is 3, 4, 5, and 6. So the Fibonacci number 4 is actually this one. OK, just so you get that straight. So Fibonacci number of n, right? And we're going to return, let's say it's an int. And we're going to make this an int, like that, int n. OK, is going to be if n equals 0, return 0. If n equals 1, return 1. And finally, otherwise you have to return fib n minus 1 plus fib n minus 2. And that's our recursive function. OK, so we've done a little recursive function here. There's a big problem with this one. And a problem not logically. This will actually work perfectly fine. OK? What is the problem with this function? Did you guys talk about that in 11? Oh, you did. You guys remember? Oh, good. Well, that's why we're reviewing. A couple people do, yeah.
It like has to keep calling itself like a lot of times.
Yeah, it has to keep calling itself a lot of times. Notice what happens. You call Fibonacci once, and that function calls it twice. And then this one calls it twice, and this one calls it twice. And then one of the ones here calls it twice, and this one calls it twice, and this one calls it twice. This is an exponential increase in the amount of stuff you're having to do. Not only that, take a look at the fact that you're doing Fibonacci of n minus 1 plus the Fibonacci of n minus 2. You're redoing a lot of these things. If I was to write this out for the Fibonacci of like 4 or 3 or something, you'd see that you end up doing Fibonacci of n minus 1 like 3 times in there. All right? And you have to redo all that calculation. We don't want to redo that calculation. Okay? What we want to do is we want to make a simpler way of using recursion to do this such that you don't end up with like crazy things that expand the number of calculations you have to do. If you were to try this on a computer and write this function just like this, and then try to put in Fibonacci of like 20, right, it would probably crash. Right? Something around 20 is going to crash this because it's an exponential increase in the number of things that it has to do, and not so good. Okay? There is a better way. All right? There is a better way. If we do the following, okay? If we say, hey, instead of making the computer recalculate all this stuff, let's actually pass some of that data along with it. Did you do this in 11? Where you went and did the new one? All right, good. Let's change this so that we have a slightly different way of keeping the values propagating through so that we don't have to recalculate them. Okay, let me do it up here. I'll start on this side over here. Okay. So here's what we're going to do. And we're going to write what I'm going to call fib helper. Okay? And fib helper is going to also return an integer, except it's going to take 3 different values. Okay? It's going to take n, which is the same n as we had before. Okay? It's also going to take a previous value. We'll call it previous value 0 or partial 0, whichever you want to put. Previous 0 and previous 1, like that. Oops, those are also integers. Make those proper. Integer n, integer p0, and integer p1, like that. Okay? Now we're going to be able to pass along all of our hard work that we do. Okay? I'm going to erase this because it almost looks like that's part of it. All right. Okay. So we're going to be able to pass along some of these details. All right. In this case, we're going to have one little base case here. Whoops. If okay, n equals 1, okay, we're going to return p1. Okay? So bear with me on this, and we'll walk through what's actually going on in a minute. But basically, if n equals 1, we're going to return this value. Okay? Otherwise, we're going to do the following. We are going to return fib helper n minus 1, p1, and p0 plus p1. Okay. Now, let's see if we can figure out what's going on here. Okay? Let's pretend we called this with 5, 0, and 1. Okay? So we're looking for the Fibonacci value of 5. Okay, let's see what happens here. Is n equal to 1 when it starts out? No. Return the Fibonacci helper of 4 and p1, which is 1, and p0 and plus p1, which is also 1. Remember the sequence. Right? The sequence looked like that. Okay? What did we calculate over here? P1 which happened to be 1, and then P1 plus P0. We calculated this one and are passing it along. Okay? Let's see what let's just go through this a little bit and see what starts to happen here. Okay? All right. We start out with 5, 0, and 1. I'll put that up here. 5, 0, and 1. Okay. If n is 1, return. So n is not 1. This is n. This is P0, and this is P1. Okay. N is not equal to 0. So we're going to return. So this, the first time we call it, returns. I'll just abbreviate here. Fib helper. Okay. N minus 1, 4, and then P1, which is 1, and then P0 plus P1, which is also 1. Okay. Let's see what happens now. This Fibonacci helper is going to return something too. It's going to say, is n equal to 1? It's not. Therefore, return fib n minus 1, P1, which is this one now, and P0 plus P1, 2. See how we're actually passing along? We start passing along the values that we're now calculating. Okay, the next one hopefully will return 2 and 3. Right? Now we say, OK, return. This one returns 2, which is n minus 1, P1, which is 2, and then P1 plus P2, which is 3. Right? Almost there, actually. Now we're returning that one. And then finally, this one returns. I'll write it up here. This one returns 1. Well, almost finally, I should say. 1, and then 3. And then 2 plus 3 is 5. And we're almost there. Now we call Fibonacci helper one more time. We've got 1, 3, and 5. Is n equal to 1? It is. So now we return. It just says return P1, which is this one. That one returns 5. This one is now 5 because it's returning what that one returned. This one returns what that one returned, which this one returned, which is 5. This one returns what this one returned, which is 5. And then this one finally returns this, which is 5. And that's our final answer, which is this one. Okay? Now, the one thing you don't want to do is you don't want to make people do this extra stuff. You kind of want to hide this. We can very easily hide this. Right? If we say, let's do this. If we say int fib n, oops, right? I'll make that int n, just like the way we did it before, just one value we're going to pass in. Okay? What you can do is you can say, OK, if n equals 0, return 0, like that. If n equals 0, return 0. Or you can say return fib helper n, 0, and 1. And that will now say, OK, if we want the Fibonacci number of n, it will go through, it'll check for the base case, right, 0. And then it will say, all right, call fib helper with n, 0, and 1, which is what we did before, and that gave us the right answer. So do you see how that kind of, you can hide the idea of this helper function to do that? Okay? I know that was kind of quick, but the whole point is we can now have a function that only calls, this one, only calls our recursion once, and it's much, much faster. This you can do Fibonacci up to like a million, well, probably thousands and thousands, maybe a million if you wanted to, right? This one, probably not a million, thousands anyway. You could call this one up to. Before the other one, you wouldn't make it more than 20 because of all that cascading of extra stuff. Okay? Any questions on that one? All right. So the only other two that we have up here, and I don't think we really have time to go through them right now, are the greatest common divisor, or divisor. Divisor? Divisor. I'll call it divisor. Greatest common divisor, right? Which says, for instance, if 25 and 20, the greatest common divisor of that is 5, because 5 is the greatest number that goes into both of those, evenly. Okay? There's a function, okay, there's an algorithm called Euclid's algorithm. There's actually a brute force way of doing this, right? The brute force way of doing this is saying, whichever one's smaller, see if that one goes into this one. And if not, make this one go down by 1, right? And then if that doesn't go into it, make it go down by another. And if that doesn't go into both of them, rather, make it go down by another, et cetera, et cetera, et cetera, all the way down to, in this case, it would get to 5. It would go into both of them evenly, and it would work out fine. Okay? There's another algorithm which is actually much better called Euclid's algorithm, which was from like 200 BC, which is way long ago, which actually goes down and does it much more easily. Yes? Oh, OK. I thought you had a question. All right. So Euclid's algorithm is actually much easier, where you actually take the remainder when you divide like the bigger one by, let's see, the smaller one by the bigger one. And no, the other way around. The bigger one by the smaller one. Take the remainder and then check that against both of them. And you can keep going down there. It saves a lot of time. But I don't think we'll have time to go through it right now. OK. And then finally, the last one here is, and by the way, you can do that recursively because you can just break it down into the same sort of idea where you break it down into parts and you can call it recursively. Maybe I'll do that first thing when we come back on the other day. The final one is palindrome. Okay, you guys know what a palindrome is, right? It's a sentence that repeats going in reverse. In other words, it's a sentence that is the same in reverse as it is going forward, right? So if we had a sentence, I'm not going to try to come up with an actual sentence. I forgot the actual sentence. But we had something like A, B, what's that? Race car? That's a good one. That is a good one. Race car. R-A-C-E-C-A-R. There we go. OK. So if you look at this is a palindrome, because if you spell it backwards, it's also race car. Very good. How might we break this into, or how might we check if this is a palindrome? Like, how would you go about trying to check and see if this is a palindrome? Ideas? Yeah.
Count how many letters there are, then check the first one to see if it's the same as the last one.
Count how many letters there are, and then check the first one and the last one. Sure. Why don't we just check the first one and the last one? Let's make it easier, right? We would have to probably count them somehow. But all you do is you check that one and you check that one, right? And if they're the same, it's still a palindrome. Then you can do this. You can get rid of those two. And then you check the next two, like that, and keep going down. And there's this funny case where either it's even or odd number of letters. And you got to make sure that if it's odd, you don't worry about the last one, right? But can you see how this might be a recursive solution? First, you do this size string. Then you do the size string minus 2, right? You chop the ends off. Then you do the same thing minus 2 and chop the ends off. And then you get to the end like that. So it can be done very nicely in a recursive fashion. Okay? It's easier to do in some languages than others. Particularly C++ is not an easy one to do it in. But I mean, because of the fact that C++ is not that great at dealing with strings. But you can do it in that. And maybe I'll show you that on Wednesday. All right, I think that's good enough for now. Any questions on the material, the homework, recursion, anything else? OK, then we'll see you guys Wednesday.